Alex, tendría que poner los dos porque
Test.
ese es para lo que te grabo
Okay.
y este es para acá adentro.
I feel like Robocop now.
Sí.
Test.
¿Está encendido?
Sí.
On. Ahí está. Listo. A ver, hola.
Test.
Sí.
Yeah, it works. So I start. All right. Hi. I am Alexandre Bergel from the University of Chile. So we talk about execution profiling, code profiling, and the idea of working on code profiling actually happened in 2009 and the last small talk, like 1 year ago. And the idea of code profiling is to help me actually to maintain some of the software that I've been developing. So I am the main developer of Mondrian, which is I think a cool visualization framework. And I've got a number of users, and those users actually want the system to be fast and to work well, to not have that many bugs. So this is why I got an interest in code profiling. So code profiling, the idea is that when you have a piece of code that doesn't do exactly the thing you want it to do, so what you have, you have someone or something that just listen at some particular events, that just listen at the execution of the program. Then you can gather some info, some data, some values, and hopefully once you start to reason on these values, then you can fix the program and try to understand why these things happen at the very beginning. So I talked a lot about code profiling last year during the Tigre. This is with Alexandre Vars. Also, we had some very nice evening at the studio place. So that was really cool, actually. So I found this picture. I couldn't resist to show them to you. And so that was last year, and I still like to have an idea of what I really wanted to have. So now I will show you what I've been doing. This year. So how comes that the thing is too short? Oh no. Anyway. Okay, so before working on a new profiler, I tried to look at what are the already existing code profiler. So code profiler, actually, the idea is not new. So the very first one appears with gprof. This is the one you can get in every C distribution. And gprof, you run, you compile your C program with some particular options, and then you can do some using gprof, the binary. Then you can inspect a bit what happens at the execution time. You can see here the list of functions and the time in seconds, and the amount of time in percentages that has been taken by each of these functions to execute. So this has been released in like 30 years ago or something, a bit more, 35 years ago. Then there were like the gprof in 84. I did like the call graph. So like here this function report called the function time local, which then called print and so on. So in 84 you had the call graph. And now if you look at the modern code profiler, this is what it looks like. So this is a screenshot taken from the Yokit website. And Yokit, this is, when you go on the website of Yokit, it is said that it's the best code profiler for Java. And when you profile an application in Java, then you can get the list of different methods that are invoking each other and the amount of time that has been taken. This is a different screenshot. Can even tell you the amount of invocations. So this is a different code profiler, gprofiler. If you go on the website of gprofiler, then you will find that this is the best profiler you can get in Java. I don't know which one is the best, Yokit or gprofiler, but apparently these guys are doing, putting some effort in getting some very nice colors and getting very nice tree to get the call graph. So this is different. You can even get some nice colors that show you the number of instances that have been created by particular classes and so on. Different screenshot. But now if we step back a bit, what but what I showed you is the fact that the information conveyed by code profiler hasn't evolved that much since gprof. You know, for each method frame that you can get on the runtime stack, then you know the amount of time this frame has been present on the core stack, which is, in my opinion, a very poor concept on getting to know what happens at runtime. So the code profiler actually are quite good in understanding what actually happened. You know, why did I spend 30% of my? It really tells you why. It tells you where I spent 30% of my execution time, but actually it doesn't really help you to understand why and how. You know, is there a slow function that is called too often? To answer this kind of question, the current profiler doesn't really help you. So often what you do is to do some ad hoc benchmarks or adding some transcript to know, yeah, this is what people do. No, also the general question of what makes a function slow. This hasn't been really addressed, I think, properly by current profiler. Okay, so this will drive a bit the following of the presentation. So first, I will talk about Polymeric View. Polymeric View, this is a very nice visualization of things, whatever. But this is, you can visualize structure and some metrics with profiling view. Then I will show a profiling blueprint, and I will say a few words about the implementation. So Polymeric View, this is the result of some work done at the University of Bern at the time by Michele Lanza. He's the author of Code Crawler, and he did some very nice things with his view. So the idea of Polymeric View is to visualize a structure on which you can map some metrics. So the idea is that a Polymeric View is a graph. So here I have 3 nodes, 1, 2, 3, and I have 2 edges. And then on such a view, then you can map up to 5 metrics. So you have the x, you have the y, this is 2, then you have the height, and the width is 4, and the color, which is the 5th. So you can add some more dimensions on this picture, such as the width of the line, the width of the border, but up to 5 metrics, Polymeric View works quite well. And I use Polymeric View to display the profiling information of what I call the Chi profiler. So this is how you will invoke it in Faro. So here I have a piece of code contained within a block, and the code example that I use is a script of Mondrian that just creates a view renderer and then create 100 nodes, and for each node it creates 100 nodes for each particular node, and then it does a layout. And actually, doing the layout, this is what it costs the most of time. So when I open a workspace, I type this piece of code, and I do it. Then after some time, then this is what I get. I get here a piece of. So what I show here is a piece of the profiling, the visualization I obtained. So here I can see some big boxes. So here, and each big box represents a class. So here I have 4 classes. So here I have MO graph elements, a subclass which is indicated by the edge here, a subclass which is MO node, and below I have MO root. And here I have MO view renderer, which is not a subclass of any of these classes. So within a class, I have methods. So each square inside this is a method. So and the way that methods are rendered, this is pretty interesting, because then I have the amount of time the method takes to execute. This is the height. The width, this is the number of times the method has been invoked. And the color, then the number of different receivers the method has been invoked on. So here I can see the very thin and tall methods. So this is actually apply layout. The method has been invoked just once, since it's very thin. It has been invoked on just one receiver, this because it's white inside, and then it's very tall, so it means that it has taken a lot of time. Actually, this is the method that took the most time of the piece of code I showed you before. And here I can see some interesting patterns, such as some very thick, tall, and black methods. So probably here, this is where I spend the most of time on the computation. And now if I want to optimize my application, then probably I will have to focus on this method here. So now I'm using, I'm profiling Mondrian. And I am the author of Mondrian. And when I was a bit surprised to see these big, large squares. So with the mouse, then I put the mouse above some of these nodes. And I was surprised to find bounds here. The bounds, this is a method defined in the class MoGraphElement. This is a method that returns me the size, then the bounds of the graphical elements. When you send a message bound to graphical elements, which could be a node or edge, then it tells you the instance of the class rectangle that contains this element. And I was really surprised to see that it takes so much CPU time here. And whereas I think that's, I was really surprised. So then I did a right click on this. Then I can do a right click on this method here, which is likely to be the root of the whole call graph, and then obtain this view. So here I have apply layout, and then I have so now here I do not see classes, but I just see invocation between different methods. So here I have the apply layout defined on the class MoRoot, and then here I see all the methods invoked by this method here. And then here like this, I can see all the whole graph of the invocation between different methods. So as before, the 8th is the number, the total amount of time the method has taken to execute. The width is the number of times the method has been executed, as before. The thing that changed here is the color. The color tells, so there are three colors. There is the gray, the white, and the yellow. The gray color tells you that the method has done a side effect. So this method here have changed the state of the program somehow. They modify some variables. The yellow means that the method hasn't changed anything. It probably hasn't changed anything. So it means that these functions here, these calls, these methods, they are likely to be functional since they do not modify anything. And then the white is that I'm not quite sure actually. It means that there are some, sometimes it was just functional, and it was just did some pure modification, where it's not really certain. And this is where there is the bound method. So here bounds is there, and this is a yellow method. It means that bounds doesn't do any side effect. And the nice, so I can do right click on this method here to have a more detailed view. And this is where bounds is. Bounds just call one method, which is shape bounds at if present. And then here I have some method that called bounds. And this method is yellow and equals just one method, which is yellow again. And the nice things of having this box here colored as yellow is that it gives me a very nice hint on how I can optimize the code. So this is the definition of the bounds method defined on the class MoGraphElement. And yeah, so because this method was painted yellow, then probably I can add here a memorization technique, such as I can augment the class MoGraphElement with a new variable called bounds cache. And here I can put the result of this of bounds within this bounds cache, and then for the second call of bounds, then this method I will just use the cache that has been computed. I mean, the idea is pretty simple. If I have some money in my pocket and someone asks me how much money do I have, I just pull out all the coins and start to count. And then once I know, I can answer to the question, how much money do I have? If I put the money in my pocket and if I do not buy anything, if nobody, robbed me, then for the next question, how much money do you have? Then I know the answer since I completed it before. This is exactly the same idea here. So just by adding these two lines here, I gain, a very nice speed up. So this is the structural blueprint I had before the optimization, and this is the blueprint I have after the optimization. So here I can see some differences between, so this is what I had bounds, and now bounds has been reduced significantly. And some nice things that, some side effect is that there are some methods that they not take more share of the CPU time consumption. Since actually here I'm not telling how much time I spend, but what is the percentage of the total execution time I spent in this method. So if I reduce some of this part here, then some other part get bigger, since I total I have to have 100%. And yeah, so again, like 43% speed up. Then, I was convinced that this works, so yeah. Sorry.
Alexandre, how do you tell whether a method has a side effect or not? It's a static analysis of the code, or is
no, this is dynamic. So actually, it's very easy. So before executing the method, then I get a snapshot of the arguments and the receiver, and this snapshot is just a XOR of each values of each hash values of the arguments and the receiver. And then if this snapshot is the same before and after the call, then it means that probably the method doesn't do a side effect. Okay, so I was pretty convinced that this idea works, so I try to push it a bit further. So this is the evolution of the behavioral blueprint. So here this is where bounds were, and then it has been reduced. Then I continue a bit to optimize Mondrian. So these bounds here actually is okay. So here I optimize bounds. Now I try to profile the UI thread of Mondrian. And this is what I had. I did exactly the same profiling, but on the UI thread, and I saw some very, very large yellow methods. Then for the same thing, I added a cache in the method absolute bounds, which gave me the same thing than bounds, but in a absolute coordinate. And then I've been able to reduce quite a lot of this method here. And again, I was not really happy about that. I tried to understand really why here is it so slow. And I noticed here there is a link. And then I just changed this link, and I was able to significantly reduce the execution time of the piece of code I've been profiling. So at that stage, it's very likely that I'm not able to optimize Mondrian anymore, and at least in a very simple manner. So probably now if I want Mondrian to be faster, then I will have to change the structure and the design of Mondrian itself. So I will say a few words about the implementation. So for this blueprint, I had to collect a number of metrics. So the first one is execution time for methods in terms of percentages. How many percentages of the total execution time this method has taken. Then the number of executions, how many times method has been invoked, and on how many different object receivers the method has been invoked on. Then I have some dynamic properties, whether method performs side effect or not. Something interesting here with these three metrics is that if I try to get one of them, then the total one becomes a bit complex to get. So if I try to understand, if I try to get the number of times the method has been executed, then it's very hard at the same time to know what is the execution time for methods, because this means that I have to insert some bytecodes that count, and this one is supposed to just work on the original body. So getting all these three at the same time is a bit tricky. So what I did is that the piece of code to be profiled is actually executed twice. The first time using the sampling method to get the execution time. This is message steady. So the piece of code I want to profile by my profiler is executed twice. The first time with message steady to get the amount of time I spend in each method, and then the second execution I do full instrumentation to get the remaining metrics. So I use the hash values to distinguish between different object receivers, and I have a kind of AOP mechanism for the low-level instrumentation, something I showed yesterday with the SPI framework. And I've done the visualization using Mondrian itself. So that was kind of, meta loop, such as in Mondrian, I visualize the execution of Mondrian itself, something I find interesting. So everything has been done in Faro. So that was what I've done last year. So we've been doing our job at publishing different forums. So it was done at last year Tools, very good conference, by the way. I recommend. And has been done in also in a journal. So we are currently submitting to a journal the last result we had in the topic. So what I plan to do for the coming year is to continue on work on this profiling. So here, this is the view that I had before, and as I say, the 8th of each method is obtained by message study. And actually, I don't like message study at all. This is really something I think we should get really rid of. I mean, there is plenty of opportunities for improvement in that. I think in that respect. So one of the problems that you have in message study is that if you do two profiling, then you do not have exactly the same result. If you now I change the computer, or I just change the virtual machine, then the profiling I had done on a particular executing context then is not valid anymore. If I just change the computer, if I opt for a new Mac, then I cannot keep track of the progress since it's not relevant anymore. And this is really a serious problem. This is really annoying. And then there has been plenty of different other problems you can get. For example, you cannot use message study to profile the VM itself when executed within the VM, something we discussed yesterday. I discussed yesterday with Elliot. And there is other problems. So there is an idea I'm currently exploring, which is counting messages as a very good proxy to estimate the CPU time consumption. So the idea is now I'm not interested in getting to know how much time I spend in a particular method, but knowing how much methods a particular method has invoked. So so I was not really sure whether it's going to work or not, but apparently I took some applications. So here there are 16 applications in Faro. So each cross is an application. So there is Mondrian, there is Moose, there is Magritte, there is Peer, there is Seaside, there is the collection framework, there is XML. And then I run the test for each of these applications. And then I counted the total amount of messages sent by running this test. And then I plot them on this scatter plot. I plotted them on this graph. So horizontally, I have the amount of time taken by the test to execute, and vertically I have the total amount of message sent for the test to complete. And the very nice thing here that I have a line, what the statistical guys call the regression line. So apparently this counting messages is a very, very effective way. So there are some issues, for example, writing the method lookup cache that okay. I call this line the regression line, and the coefficient director of this line is called MR, message rate. Message rate for an application called Alpha and in a context C. And the message rate actually is not constant in time, so probably at that, around that level is probably due to the warming of the cache. Then it seems to be stabilized over the time. And okay, so I think it was a pretty good start. Then I tried to keep a bit further on that. So now I do not focus only on one application, on the application, but on each method of a given application. So in that case, this is Mondrian. So now I'm profiling Mondrian, and each cross is a method of Mondrian. And vertically, I have the amount of messages sent by the method. And vertically, the amount of time this method has taken. And again, this is by running all the tests of Mondrian. And then again, I see that all these methods form, a line. So yeah, this is. So I think it's pretty. I think it's a good start. So there are plenty of things that we can do now. For example, doing some estimation with the primitives, because primitives, even though they are fast, usually they do not take exactly the same amount of time. So probably there are things that can be done. And something interesting actually that I discovered that if you take one piece of code, if you execute it twice, it might not send exactly the same amount of messages. And the reason why is, one of the reasons is, for example, the hash values. So if, the thing is, a dictionary uses the hash value of the object to be inserted within the dictionary, and the hash value, this is given by the virtual machine. And since at the two execution of the same piece of code, then the object inserted in the dictionary might not have the same hash. So it means that I might have some slight differences. But the differences between the variation that I have on the number of message sent is much smaller than the one I can get on the time.
Alexandre, how long did it take you to figure that out?
At the very beginning, I thought it was a bug in my implementation. But then, just happened after a coffee break in, Ricardo? No. Yeah, please go ahead.
Just what is that one off on the side?
Okay, so I don't really know. I mean, this is like fresh work, I need to spend some time. I don't know whether it's an error of my profiler or whether this has been, I don't know. So it means that this method here actually has sent a lot of messages, but it has taken a few time. Maybe it's because of some optimization by the compiler. I have no clue. I need to figure out.
You don't know which method it was?
Yeah, I can get, but it's going to be ready for the next smalltalk. I promise I will tell you more about that. Okay, so I like this idea of profiler. So this is just one dimension of my work. So there is some other dimensions. There is, for example, the work done by Felipe on differentiation profiling. So usually when you want to do, when you want to understand what happens during the execution of a program, what you often do is to add some lines, remove some lines, compile, and try again. And and then you can see what are the differences in terms of execution time. So the idea that Felipe had. So Felipe is over there. Move your hand, Felipe. This is my student. And so the idea that he had, actually is quite neat, is to keep track of the progress against the evolution of the different versions of the softwares. So the problem I had is that I have Mondrian. There is almost 600 versions of Mondrian, and around the version 300 something of Mondrian, then I made an optimization, and over the time this optimization seems to to go into nature. I didn't know where the 30% just went. The Mondrian was getting slow again. So the idea of Felipe is to show the call graph of a particular method here. In that case, apply layout, the same than before. The 8th is the amount of time taken by the method to execute. The width, the number of time the method has been executed. But something like different than the profiling I said before is now the color here tells you whether this method here is faster or slower than the previous version of Mondrian. So because here it's pink, it's light red, it means that the method is slower. But the source code is identical source code. It doesn't change. And here is strong red. It means that this method here is slower because it's red. But since it's strong red, it means that the source code has changed. And that's this is very, very smart, I think. Apparently nobody has worked on that before. And then you have the green saying that this method is faster than before, and the yellow method didn't exist in the previous version. Then, okay, so I think this is a very, very good path for future work. So there is the test coverage. So Fabian, where is Fabian? Fabian, move your hand. So Fabian is also another student of me, and is getting some interest in test coverage. So something I showed actually yesterday. I don't know whether you've been there or not, but I really feel that for code coverage there is really something that can be done. Most of the test coverage that we have around are pretty simple. They will just tell you the amount of percentages of the method that have been covered or not, which is really poor. You know, some more refined one can tell you the amount of statements, whether the statements that have been covered or not. But actually covered is very, you know, it's very, very vague. What does it mean that the method has been covered or not? So what I have here in this visualization is each method here, the 8th is the number of lines of code that define the method. The width is the number of time the method has been invoked. And the color is the amount of object the method has been invoked on. And when the method is red, it means that the method hasn't been invoked. So I got this profiling after running all the tests. So this is an example of Metacello. So I run all the tests of Metacello, and then I got this blueprint. And so this method here hasn't been executed by the test. And this method here that are very tall, it means that this method has a lot of lines of code. It's very thin. It means that the method hasn't been executed that often. And then it's light. I mean, the color is very bright. It means that it hasn't been executed on that many objects. Probably now if I want to enhance my test, probably I want to test this method further, because this method is apparently complex, it is tall, and hasn't been executed that often.
What do you mean in as many objects?
Sorry?
The width, I think it is, and how many objects it has been.
No, the width is the number of times the method has been executed. And then the color is on how many different objects the method has been invoked on.
Number of objects? The different classes of receiver.
Yeah.
That's the question.
No. It's not the class. This is the object. On how many different objects?
Different instances.
Yeah, instances. So I'm pretty sure that this visualization can be enhanced, but I think this is a very good start. And then there is the work done by Mariano Abelcoca. Move your hand. This is Mariano, and he has been working on a further profiler, which is about memory profilers. So this is again an example of Metacello. Metacello is very slow, and it takes a lot of memory. And this is a method current version. And here I have the call graph, and the size tells you about the amount of memory this method has taken. And since it's yellow, it means that the method is functional and it doesn't do a side effect. So probably adding a cache on this method is very useful. Okay, so this is what I want to tell you today. So thank you very much. Just wanted to say that SPY is available, of course, on the Moose website, but also on QuickSource. These two graphs has been obtained with some collaboration with Romain Robes from the University of Lugano, and now he's at the University of Chile, with me and Walter Binder from the University of Lugano. And I would like to thank Mariano, Fabian, Felipe, and all the students I have in my lectures. So thank you very much.
I was wondering about the visualizations you use there. One of them is that the classes are very prominent. Do you find that important in visualizing the profile? I mean, the thing that I miss a little bit is the containment of that. We have a long method and thing, but the time expressed there, a lot of it is the other blocks around. I guess a little bit the time aspect, where the time actually went. You have the same chunk of time repeated on the graphs over and over again, so I don't get a very good sense of. How did you find that the class of emphasis is important in getting a good sense of it, or is it something that?
Okay, so far, yes and no. Usually, when I program, and I often use this visualization. But this visualization, could be useful to check out, to find out what are the classes that are responsible for major slowdown. This class is obvious. But then, if this class has been written by someone, probably I should ask him.
You just mouse over and you get the information there. So to me, to me, the important aspect of the visualization
is the timeline.
Get the notion of,
the flow.
Yeah, so I was wondering if you find particular advantage in those particular way to organize and visualize the information, but it's maybe something that you guys are still thinking about.
Exactly. So apparently it seems that the visualization is more useful than this one. But probably, there are some different ways to reorganize, to reorder the methods, and something that I think some further works, and indeed it. Indeed.
Do you plan to include statistics about, say, how many times the garbage collector are running, or in case of virtual machines like COG or VisualWorks or whatever, the number of times that the native stack is still going to the object memory and things like that?
Okay, so about the garbage collector, Mariano is going to talk about that a bit later on at 6, right? 6 o'clock? Yeah, it's going to be at 6, I think 6 o'clock. And so this is one thing. Then about but obviously there are a number of metrics I would like to extract. For example, here maybe interesting to know what are the different things related to the JIT, whether the method are about the lookup, whether the method called cache, how many missed hits do I have. Those are the metrics that I would like maybe to explore. But yeah, there's some number of works that has to be pushed further. Okay, so thank you very much.